Alright, this is the second part of the MLIR paper, Scaling Compiler Infrastructure for Domain-Specific Computation. We read until page 3, little built-in, everything customizable, that's parsimony, then proximity, and also traceability. Such a genius I am. I'm a genius. Anyways, we're gonna keep reading through this. So I'm gonna finish it and then probably analyze it after we have finished reading this. Alright, and that's gonna be probably in a few other parts. I tried to keep it as short as possible, but we'll see how it goes. Alright. So what we read was that basically we have different languages, and then these different languages have compilers, different versions of their compilers to run on different machines, and MLIR tries to be this generic thing that can generic design that you can use to have these languages basically communicate with the right architecture with no overhead of basically writing a new compiler. So it's basically adding a layer to remove layers. Alright, so let's just start from this paragraph here. Little built-in, everything customizable, parsimony. The system is based on a minimum number of fundamental concepts, leaving most of the intermediate representation fully customizable. A handful of abstractions, types, operations, and attributes, which are the most common in IRs, should be used to express everything else, allowing fewer and more consistent abstractions that are easy to comprehend, extend, and adopt. Broadly, customizability ensures the system can adapt to changing requirements and is more likely to be applicable to future problems. In that sense, we ought to build an IR as a rich infrastructure with reusable components and programming abstractions supporting the syntax and semantics of its intermediate language. Basically, I think from this paragraph, parsimony part is that the intermediate representation of the language should be customizable. So if you're writing a language or you're designing a backend, then you can use MLIR to make your design decisions better. A success criterion for customizability is the possibility to express a diverse set of abstractions, including machine learning graphs, ASTs, mathematical abstractions such as polyhedral, control flow graphs, and instruction level IRs such as LLVM IR, all without hard-coding concepts from these abstractions into the system. Certainly, customizability creates a risk of internal fragmentation due to poorly compatible abstraction. So it creates a risk of internal fragmentation due to poorly compatible abstractions. While there is unlikely a purely technical solution, the system should encourage one to design reusable abstractions and assume they will be used outside of their initial scope. SSA and regions. Again, parsimony part that basically cares about customizability of your intermediate representation. The static single assignment SSA form is a widely used representation in compiler IRs. It provides numerous advantages, including making data flow analysis simple and sparse. It is widely understood by the compiler community for its relation with continuation passing style, and it's established in major frameworks. As a result, the IR enforces the value-based semantics of SSA. Its referential transparency and algorithmic efficiency all considered essential to a modern compiler infrastructure. However, while many existing IRs use a flat linearized CFG, representing higher level abstractions, pushing introducing nested regions as a first class concept in the IR. This goes beyond the traditional region formation to lift higher level abstractions. Loop trees, speeding up the compilation process or extracting instruction, or SIMD parallelism. Okay, so SIMD, I believe we use Notion. Here we go. Okay, we already have this, so let's assign SIMD parallelization. Here we go. Single instruction, multiple data is a type of parallel processing in Flynn's taxonomy. SIMD can be internal part of the hardware design. It can be directly accessible through an instruction set architecture, but it should not be confused with an ISA. SIMD describes computers with multiple processing elements that perform the same operation on multiple data points simultaneously. Okay. It can be directly accessible through an instruction set architecture, but should be not confused with an ISA itself, the instruction set architecture. SIMD describes computers with multiple processing elements that perform the same operation on multiple data points simultaneously. Such machines exploit data level parallelism but not concurrency. There are simultaneous parallel computation, but each unit performs the exact same instruction at any given moment, just with different data. SIMD is particularly applicable to common tasks such as adjusting the contrast in a digital image or adjusting the volume of digital audio. Most modern CPU designs include SIMD instructions to improve the performance of multimedia use. SIMD has three different subcategories in Flynn's 1972 taxonomy, one of which is SIMT. SIMT should not be confused with software threads or hardware threads, both of which are task time sharing. SIMT is true simultaneous parallel hardware level execution. Alright, so I'm a little bit curious about Flynn's taxonomy. Flynn's taxonomy is a classification of computer architectures proposed by Michael J. Flynn in 1966 and extended to 1972, and classification system has a stock. This classification system has a stock and has been used as a tool in the design of modern processors and their functionality. Since the rise of multiprocessing central processing units, a multi-programming context has evolved as an extension of the classification system. Vector processing, covered by Duncan's taxonomy. Vector processing, covered by Duncan's taxonomy, is missing from Flynn's work because the Cray one was released in 1977. Flynn's second paper was published in 1972. This seems a big deal. I'm going to come back to this later in probably a separate video, but it's good to know that. Let's first search what taxonomy is. Okay, so basically taxonomy is the branch of science concerned with classification, especially for organisms. So probably it has to do with Flynn's taxonomy. The classification of computer architectures. The classification system has a stock and has been used as a tool in the design of modern processors and their functionality since the rise of multiprocessing central processing units. A multi-programming context has evolved as an extension of the classification system. Vector processing is missing from Flynn's work because the Cray one was released in 1977. Okay. Alright, maybe we don't need to come back to this. We can just do it right now. Differential classifications defined by Flynn are based upon the number of concurrent instruction or control streams and data streams available in the architecture. Flynn defined three additional subcategories of SIMD in 1972. Single instruction stream, single data stream, single instruction streams, single data stream. A sequential computer which exploits no parallelism in either the instruction or data stream, single control unit fetches a single instruction stream IS instruction stream from memory. The CU then generates appropriate control signals to direct the signal processing element to operate on a single data stream. An example, one operation at a time. Okay. Traditional unit processor machines like older personal computers and mainframe computers. So now we have single instruction stream, multiple data streams. Interesting. A single instruction is simultaneously applied to multiple different data streams. Instructions can be executed sequentially, such as by pipelining, or in parallel by multiple functional units. Flynn's 1972 paper subdivided SIMD down into three further categories. Array processor, these receive the one same instruction, but each parallel processing unit has its own separate and distinct memory and register file. Pipeline processor, excuse me, let me just catch my breath. Alright, so pipeline processor, these receive the one same instruction but then read data from a central resource. Each processes fragments of that data, then writes back the results to the same central resource. In figure 5 of Flynn's 1972 paper, that resource is main memory. For modern CPUs, that resource is now more typically the register file. Alright, okay, so SIMD, single instruction, single data stream, multiple instruction, single data stream, and single instruction, multiple instruction, so multiple instruction, single data stream, multiple data stream, multiple instructions, multiple data stream. Right. Okay, so associative processor, those receive the one same instruction, but in each parallel processing unit, an independent decision is made based on data local to the unit as to whether to perform the execution or whether to skip it. In modern terminology, this is known as predicted masked SIMD. Array processor, the modern term for an array processor is single instruction, multiple threads. SIMT. This is a distinct classification in Flynn's 1972 taxonomy. As a subcategory of SIMD, it is identifiable by the parallel subelements having their own independent register file and memory, cache and data memory. Flynn's original paper cites two historic examples of SIMT processors, Solomon and ILIAC 4. NVIDIA commonly uses the term in its main marketing materials and technical documents where it argues for the novelty of its architecture. Solomon predates NVIDIA by more than 60 years. Alright, they just told NVIDIA to pipe down. The Aspects Microelectronics Associative String Processor, ASP, categorized itself in its marketing material as massive wide SIMD, but had bit level ALUs, arithmetic logic units, and bit level predication. Flynn's taxonomy. Associative processing in each of the 4096 processors had their own registers and memory. Excuse me. Flynn's taxonomy, array processing, the line dancer released in 2010 contained 4096 2-bit predicated SIMD LAUs, each with its own content addressable memory, and was capable of 800 billion instructions per second. Wow. Line dancer, the line dancer. Aspects ASP, micro associative string processor. Associative array SIMT processor predicates NVIDIA by 20 years. Alright, so we can kind of get the idea of that. MLIR is related to breaking down instructions and basically trying to achieve a distributed and parallel computing system. Single instruction, multiple data stream, SIMD. The modern term for associative processor is predicated or masked SIMD. Some modern designs, GPUs in particular, take features for more than one of these categories. GPUs of today are SIMT, but also are associative. Each processing element in the SIMT array is also predicated. What does it mean for array to be predicated? Predicate is a function that returns a true or false value based on some condition. Okay. Multiple instruction streams, single data streams. Multiple instructions operate on one data stream. This is an uncommon architecture which is generally used for fault tolerance. Heterogeneous systems operate on the same data stream and must agree on the result. Examples including space shuttle flight control computing. Oh, interesting. So you have multiple computers calculating the same thing, single data stream, and then they should all get to the same conclusion. Make sense? Multiple autonomous processors simultaneously execute different instructions on different data. MIMD architectures include multi-core superscalar processors and distributed systems using either one shared memory space or distributed memory space. These four architectures are shown below visually. Each processing unit is shown for a unicore or multi-core computer. I believe P was up here, yeah. P processing unit, I feel like that's what it stands for. Okay, so I think we get what SIMD is now. Or SIMD oh, come on. That wasn't nice. That's not nice. Okay. Just make it one more. Okay. I believe we were here. To support heterogeneous compilation, the system has to support the expression of structured control flow, concurrency constructs, closures in source languages, and many other purposes. One specific challenge is to make CFG-based analysis and transformations compose over nested regions. In doing so, we agree to sacrifice the normalization and sometimes the canonicalization properties of LLVM. Being able to load a variety of data and control structures into a smaller collection of normalized representation is key to keeping compiler complexity under control. The canonical loop structure with its pre-header latch body is a prototypical case of a linear control flow representation of a variety of loop constructs in front-end languages. We aim at offering users a choice, depending on the compilation algorithm of interest of the path in the compilation flow. Nested loops may be captured as nested regions or as linear control flow. By offering such a choice, we depart from the normalization only orientation of LLVM while retaining the ability to deal with high-level abstractions when it matters. In turn, leveraging such choices raises questions about how to control the normalization of abstraction, which is the purpose of the next paragraph. In turn, leveraging such choices raises question about how to control the normalization of abstraction, which is the purpose of the next paragraph. I might need water later for my voice, but I think we can keep going right now. Maintain higher level semantics, progressivity. The system needs to retain the information and structure that are required for analysis or optimizing performance Attempts to recover abstract semantics once lowered are fragile, and shoehorning this information at low level often invasive. Example, all passes need to be revisited in the case of using debug information to record the structure. Instead, the system should maintain the structure of computations and progressively lower to the hardware abstraction. The loss of a structure is then conscious and happens only where the structure is no longer needed to match the underlying execution model. For example, the system should preserve the structured control flow, such as loop structure, throughout the relevant transformations. Removing this structure, an example to a CFG, essentially means no further transformations will be performed that exploits this structure. The state of the art in modeling parallel computing constructs in a production compiler highlights how difficult the task may be in general. Alright, just kind of ran through all of this. Cannot explain it. But I believe if we get to the bottom of the paper and do more analysis and try to understand LVM a little bit better, then we can kind of glue pieces together and make a whole image. As a corollary, mixing different levels of abstraction and different concepts in the same layer is a key to allowing a part of the representation to remain in higher level abstraction while another part is lowered. This would enable, for instance, a compiler for a custom accelerator to reuse some higher level structure and abstractions defined by the system alongside with primitive scalar vector instructions specific to the accelerator. Another corollary is that the system should support progressive lowering from the higher level representation down to the lowest level, performed in small steps along multiple abstractions. The need for multiple levels of abstraction stems from the variety of platforms and programming models a compiler structure has to support. Previous compilers have been introducing multiple fixed levels of abstraction in their pipeline. In an example, the Open64 world representation has 5 levels, as does the C-Lang compiler, which lowers from ASTS to LVMIR to selection directed acyclic graph to machine insta and to NC insta. More flexible designs are required to support extensibility. This has deep implications on the phase ordering of transformations, as compiler experts started implementing more and more in transformation passes. Complex interactions between these passes started appearing. It was shown early on that combining optimization passes allows the compiler to discover more facts about the program. One of the first illustrations of the benefits of combining passes was to mix constant propagation, value numbering, and unreachable code elimination. Alright. We're talking a lot about the abstraction stuff, which is what they showed. This is their whole new technology. Let's continue here. Declaration and validation, parsimony and traceability. Defining representation modifiers should be as simple as introducing new abstractions. A compiler infrastructure is only as good as the transformations it supports. Common transformations should be implementable as rewrite rules expressed declaratively in a machine analyzable format to reason about properties of the rewrites such as complexity and completion. Rewriting systems have been studied extensively for their soundness and efficiency and applied to numerous compilation problems from type systems to instruction selection. Since we aim for unprecedented extensibility and incremental lowering capabilities, this opens numerous avenues for modeling program transformations as rewrite systems. It also raises interesting questions about how to represent the rewrite rules and strategies, and how to build machine descriptions capable of steering rewriting strategies through multiple levels of abstraction. The system needs to address those questions while preserving extensibility and enforcing monotonic and reproducible behavior. The openness of the ecosystem also calls for an extensive validation mechanism. While verification and testing are useful to detect compiler bugs and to capture IR invariants, the need for robust validation methodologies and tools is amplified in an extensible system. The mechanism should aim to make this easy to define and as declarative as practical, providing a single source of truth. A long-term goal would be to reproduce the success of translation validation and modern approaches to compiler testing, both are currently open problems in the context of extensible compiler. Source location tracking, traceability. The provenance of an operation, including its original location and applied transformations, should be easily traceable within the system. This intends to address the lack of transparency problem common to complex compilation systems, where it is virtually impossible to understand how the final representation was constructed from the original one. This is particularly problematic when compiling safety critical and sensitive applications, where tracing, lowering, and optimization steps is an essential component of software certification procedures. When operating on source code such as cryptographic protocols or algorithms operating on privacy-sensitive data, the compiler often faces seemingly redundant or cumbersome computations that embed security or privacy property not fully captured by the functional semantics of the source program. This code may prevent the exposure of side channels or harden the code against cyber or fault attacks. Optimizations may alter or completely invalidate such protections. This lack of transparency is known as WYSINYWYX in secure compilation. One indirect goal of accuracy propagating high-level information to the lower levels is to help support secure and traceable compilation. IR design is the third part. So second part was design principles. The second part was design principles. Third part is, if I'm not wrong, I skipped through some stuff. Looks like I skipped. Oh, IR design, and that was design principles. Alright. Okay, our main contribution is to present an IR that follows the principles defined in the previous section. This is what MLIR does, and we review its main design points in this section. MLIR has a generic textual representation example in Figure 3 that supports MLIR's extensibility and fully reflects the in-memory representation, which is paramount for traceability, manual IR validation, and testing. Extensibility comes with the burden of verbosity, which can be compensated by the custom syntax that MLIR supports. For example, Figure 7. That's Figure 3. Figure 5. Here we go. Affine loops are operations with regions only loop. Okay, so affine for argument 0 close to 0 to only loop invariance values, loop iterators, and affine functions of those are allowed. Affine for argument 1 equals to that, so that's an inner loop. And then from there we have just loading with memory references, and affine dialect representation of polynomial implication. C I plus j is plus equal, so just putting everything in back in there. I a I b j. So add function, multiple function, F32. Where's F32? Okay. So SSA, representation of a TensorFlow graph in MLIR. I'm not sure what that is, but SSA we had it. So SSA. Static symbol assignments based IR data structures, providing a declarative system for defining IR dialogues, and providing a wide range of common infrastructure, including documentation, parsing, and printing logic. Alright. Alright. The loss of structure is then conscious and happens only where the structure is no longer needed to match the underlying execution model. For example, are we here? No, around here. Here. Alright, so we've jumped to figure 7. That's where we went. They were like two affine, whatever affine is. And we had the ci plus j, whatever, plus equal ai multiplied by b j index. I'm not sure if j is the index, but b was a function because it wasn't the the square brackets. Alright, so for example, figure 7 illustrates the user-defined syntax for figure 3. Figure 3. Alright, so we are mapping some values first. And then we have map 3. OPS may have regions attached. Affine.4. Regions consist of a CFG of blocks with arguments. Block or list of operations. Affine 4, argument 0, power sign. BB 0, argument 5, to index for operations use and define type values which obey SSA. Alright. Okay, so what happens to this? For example, figure 7 illustrates the user-defined syntax for figure 3. So the other part was the syntax of figure 3. Figure 7 was the syntax for figure 3. Okay. Operations, the new unit of semantics in MLIR, is an operation referred to as OP. Everything from instruction to function to module are modeled as OPs in this system. MLIR does not have a fixed set of operations but allows and encourages user-defined extensions according to the parsimony and everything customizable principles. The infrastructure provides a declarative syntax for defining operations based on table 19. This is something they definitely. Oh, what did I do? Can you just open this, please? Let me preview why. Let's just click it. I don't know. So this table gen for LLVM. Right, looks like a lot of LLVM. It looks like a lot of compiler stuff. Looks like registers, the operations. Not sure 100%, but looks like it. Alright, so let's just have the introduction of this. TableGen's purpose is to help a human developer maintain records of domain-specific information because there may be a large number of these records. It is specifically designed to allow writing flexible descriptions and for common features of these records to be factored out. This reduces the amount of duplication in the description, reduces the chance of error, and makes it easier to structure domain-specific information. The TableGen front-end parses the file, instantiates the declarations, and hands the result off to a domain-specific backend for processing. Alright, so program is reference for an in-depth description of TableGen. TableGen description to C++ code for details on the *TableGen commands that run the various flavors of TableGen. The current major users of TableGen are the LLVM target independent code generator and the client diagnostics and attributes. Alright. Oh, here you go. 19. I feel like that's. Oh yeah, here we go. I can make this. Oh, come on. Please. Okay, perfect. Operations see figure 4 have a unique opcode, a string identifying an operation and its dialect. Ops take and produce 0 or more values called operands and results respectively, and these are maintained in SSA form. Single static association. SSA. Static single assignment. Static doesn't change later. Single as an assignment to the single SSA, single assignment, single SSA, single as an assignment, but it's a static. Alright, so let's just go back to the 19th thing. Perfect. Okay, ops take and produce 0 or more values called operands and results respectively, and these are maintained in SSA form. Values represent data at runtime. Alternatives have been proposed aiming for higher conductivity, soundness guarantees, and better interoperability with higher level languages. This is still a subject of active design discussions. Okay, so MLIR generic representation for polynomial multiplication using affine and STD standard dialects. So similar to LLVM, because I remember LLVM had dialects in its IR. The same IR is displayed with custom syntax figure 7. Oh, come on. Oh, this is the figure 3. Operation OP is a main entity in MLIR. Operations contain a list of regions. Regions contains a list of blocks. Blocks contains a list of operations, enabling recursive structures. And have a type that encodes the compile time knowledge about the data. In addition to an opcode, operands, and results, ops may also have attributes, regions, successive blocks, and location information. Figure 3 illustrates values and ops. Or the operations here. Okay, so lower bound, it's function returning a number. I guess step 1, index upper bound that. Excuse me. Alright, the generic Quick syntax. Attributes are found in brace enclosed comma separated list of pairs. Figure 3 uses attributes to define. Okay, so leaky ReLU operation. So some TensorFlow stuff. If they were using it at Google, I guess. Oh, it is. It's lit. I don't remember. Some language. I don't know what this is. What language is this? Excuse me. Operation Definition Syntax, ODS, provides a concise way of defining new operations in MLIR. Here, one defines the leaky value operation, taking a tensor and a floating point value, and returning a tensor of the same type as the input one. Bounds of a loop that are known to be constant affine forms. Lower bound goes this to this, step that. Next upper bound that to that, where lower bound is an example of an attribute name. The brackets to that notation is used for inline affine forms. I'm not getting this affine, but let's continue. In this case, producing an affine function producing a constant zero value, the map notation is used for attribute aliases, which allows associate attribute values with a label up front. Attributes derive their meaning either from the operation semantics or from the dialect. Section 3. Section 3. Why did we jump here? Not sure why we jumped here, but not sure. Okay. As with opcodes, there is no fixed set of attributes. Attributes may reference foreign data structure, which is useful for integrating with existing systems. Example, the contents of known at compiler time data storage in an ML system. Location information. MLIR provides a compact representation for location information and encourages the processing and propagation of this information throughout the system following the traceability principle. It can be used to keep the source program stack tree that produce an operation to generate debug information. It is standardized the way to emit diagnostics from the compiler and is used by a wide range of testing tools. Location information is also extensible, allowing a compiler to refer to existing location tracking systems, high-level AST nodes, LVM style file line column addresses, dwarf debugging info, etc. Alright, let's see how much we covered. Okay, so this is the last part. This paper is going to be the last. This page is going to be the last page of this video. Now I think we're going to have 2 more to finish the paper itself. Figure 3 is a loop with the single block body attached as a region located between and delimiters. The operation specifies the flow of control across regions. In this example, the body is executed repeatedly until the upper bound is reached. The body of each region is a list of blocks, and each block ends with a terminated operation. They may have successive blocks to which the control flow may be transferred. Each terminator, example switch, condition branch, or unwind, define its own semantics. It may choose to transfer the control flow to another block in the same region or return it to the operation closing the region. The graph of successors defines a CFG, allowing standard SSA-based control flow within a region. Instead of using nodes, MLIR uses a functional form of SSA. I remember SSA, static single assignment, where terminators pass values into block arguments defined by the successor block. Each block has a potentially empty list of type block arguments, which are regular values and obey SSA. The semantics of terminator operations define what values the arguments of the block will take after the control is transferred. For the first entry block of the region, the values are defined by the semantics of the enclosing operation. For example, affine.4 uses the interblock argument percentage sign argument 4 as loop induction variable. Finally, this explicit graph design and the extensibility of operations is reminiscent of the sea of nodes representation. This connection is intentional and has been a major influence for the selection of MLIR's flavor of SSA. Value dominance and visibility. Operations can only use values that are in scope, visible according to SSA dominance, nesting and semantic restrictions imposed by enclosing operations. Values are visible within a CFG. What's CFG? Control flow graph. And right here. CFG. Value dominance and visibility. Operations can only use values that are in a scope, visible according to SSA dominance, nesting, and semantic restrictions imposed by enclosing operations. Values are visible within a CFG control flow graph if they obey standard SSA dominance relationships, where control is guaranteed to pass through a definition before reaching a use. Region-based visibility is defined based on simple nesting of regions. If the operand to an operation is outside the current region, then it must be defined lexically above and outside the region of the use. This is what allows operations within an affine.4 operation to use values defined in outer scopes. MLIR also allows operations to be defined as isolated from above, indicating that the operation is a scope barrier. Example, the std.func operation defines a function and it is not valid for operations within the function to refer to values defined outside the function. In addition to providing useful semantic checking, a module containing isolated from above operations may be processed in parallel by an MLIR compiler, since no use def chains may cross the isolation barriers. This is important for compilation to utilize multi-core machines. All these design choices highlight the proximity principle while erring on the side of parsimony, with a concept does not appear to be generic and essential enough to be built in. Alright, and then we move to symbols and symbol tables, and I feel like that's good for the second part, and we are going to do the rest of the paper in another 2 videos.